everybody, welcome back. Sorry for the delay. We didn't have any colored chalk, and everything is generated color, so I wanted to grab some chalk from the office upstairs. So now we have chalk, we can continue now with Maria's talk.
Okay, so I want to start by going over a couple of things that I kind of did quickly last time. I'm going to go from there. So last time, so yesterday we defined the cohomology ring for a CW complex. And we looked at the cohomology ring of the Grassmannian, and we, the generators are in correspondence with the Schubert cells. So we found that we take the Schubert cell decomposition of the Grassmannian. It has some Z basis. Indexed by partitions, which I'm going to call sigma lambda. And I wrote this as the cohomology class of a Schubert variety. And then I want to point out this is a graded ring. If you take, so this is in degree 2 times the size of lambda. And so if you multiply 2 of these, you're going to add the degree that they appear in. And we said that this is something I just sort of said without any justification, that when you multiply, the multiplication in this ring corresponds to intersection of the Schubert varieties. For different flags. Enough. Okay, so I just want to give a little bit of an intuition for what this cohomology class means when I say the cohomology class of a Schubert variety. Here we're actually thinking of these classes as formal linear combinations of algebraic subvarieties of the Grassmannian. So we're thinking of cohomology classes as formal combinations of algebraic subvarieties up to rational equivalence. And rather than define all of this, since I still want to keep this sort of just the basic facts kind of abstract, let me just give you an example of things that can be obtained from one another by rational equivalence. For instance, in P2, so we can consider, we looked at conics in P2 before, and the different kinds of conics you can get, that most of them are equivalent to each other under projective transformations. But if you consider, say, the hyperbola xy minus z squared is 0 as a homogenized hyperbola, you can sort of degenerate this into 2 lines by moving these sort of closer and closer to the 2 axes until you kind of degenerate it into 2 separate axes. The way you would do this algebraically is you kind of consider the family of curves xy minus tz squared equals 0. And here's t equals 1, and then we take t going to 0, and in the limit we get xy equals 0, which is just a union of 2 lines. And we say that union of 2 lines is sort of in the same cohomology class as the hyperbola that we started with. So this is an example of something you can get, and I'm pointing this out because when I talk about the Littlewood-Richardson rule, which is the rule for multiplying these Schubert classes with some coefficients here, you have to be careful not to think of this as the intersection of Schubert varieties is the union of Schubert varieties. It's the class of the union of Schubert varieties. So it's, maybe it looks like this, but it degenerates into a union of Schubert varieties according to this formula, right? So this is saying the class of the intersection of two Schubert varieties for transverse flags in this case is the sum of the classes of, so I guess I could say it's the union, or the class of the union of some number of copies of each omega nu, where here nu might appear more than once in this union, just according to this multiplicity, but with different flags. So f to the nu, say. But it doesn't mean that the intersection of Schubert varieties is a union of Schubert varieties. So that actually makes the zero-dimensional case pretty interesting, because then they are just the number of points, and you know exactly what it looks like. And in the higher dimensional cases, it's harder to say what Schubert varieties look like, what the intersections look like. There's also another fine point I wanted to point out that was a mistake from last time that Jake Levinson pointed out to me, and also Touchant, sitting over there, pointed out a counterexample of something I said. So in the case when you're intersecting two Schubert varieties, it suffices to take F and E to be transverse flags. For the Littlewood-Richardson rule to hold. But if you have an intersection of more than two, if we're doing, say, a product of three of them, then pairwise transverse isn't actually enough. So the fact is that the Littlewood-Richardson rule holds for sufficiently general flags, meaning some open subset of sort of the space of all flags. And we're going to define the flag variety today, so then we'll be able to really rigorously say what that means. Okay, so that's clarifications from last time. And so, as I promised, now we're going to talk about why this cohomology ring is the same as the ring of symmetric functions, where you eliminate some of the Schur functions. Okay, so the claim is that the cohomology ring of GRNK is the ring of symmetric functions, do more than one, mod the ideal generated by the Schur functions whose partition is not contained in the k by n minus k box. And so this isomorphism, as we said, takes the cohomology class sigma lambda to the Schur function S lambda. And this is going to give us our Littlewood-Richardson rule. So to show this, why is this? So first we have to show that these sort of multiply by this in the same way as the Schur functions, but it suffices to show it just for the Pieri case, the Pieri rule that Jeff talked about the other day. So it suffices to show that if you take the class of just a single row partition, say, sigma r times sigma mu for some mu, then this is going to be the sum over all partitions nu, so that nu skewed by mu is a horizontal strip of size r in the important box. Okay, and I don't think I'm using exactly the same notation as Professor Remmel did, but I just mean that if you take a partition nu and a partition mu inside of it that we cut out, I want the result to be a union of rows that don't overlap in the same column. So this is the rule that we had for multiplying an elementary symmetric function by a Schur function. And this is, yeah.
The ideal, shouldn't it be not contained?
Yeah. Thanks. Yeah, we're taking the things that do fit inside as the things that are in here. Good. Okay, so this is what I mean by a horizontal strip. Is any skew shape that's just a union of rows that with no two boxes in the same column. Okay, so this is analogous to the Peary rule ER times S mu, right? It's the same sum. So it suffices to show this because the ERs are algebra generators for the ring of symmetric functions, and so that tells us how they multiply by shear functions. And using this rule, you can express any sigma mu in terms of sigma r, basically by rederiving the Jacobi-Trudy formula. So this is sufficient. So we're going to show the Peary rule geometrically. Okay, so let's first, to show this, we want to rephrase it in terms of a zero-dimensional intersection and then use the duality theorem. So, in fact, we're going to use the duality theorem basically to rewrite it immediately. So let's do a proof of, this is going to be a proof sketch of the Peary rule. So the idea is let's multiply both sides of this equation by another Schubert class and see what it does to this side so that we sort of fill up the whole important box. So here, for instance, if mu is this, if mu is this inner shape and we know r, we're going to try to multiply by another shape lambda that sort of fills up the whole box and see when that occurs. By the duality theorem, which remember said that if two partitions are complementary, then the intersection of their Schubert varieties is 1 point. And if they're the same size and they're not complementary, then it's empty. So by the duality theorem, we just need to show that if we multiply by lambda, we want to show that this is something. So we know this is something times sigma b, because we're making lambda have size of lambda plus r plus size of mu is k times n minus k. And so sigma b is the only partition of the total size. So that's the only partition that can occur on the right. But then we want to know what the coefficient is, and we want to show the coefficient, which is the coefficient of sigma lambda in this product by the duality theorem. We want that it's 1 if our lambda that we chose has the property that lambda c mod mu, of lambda c here, the complement of lambda. Lambda c mod mu is a horizontal strip of length r and 0 otherwise. Okay, so let's translate this into Schubert varieties. We have omega lambda of some flag intersect with omega mu of some other flag, let's call it E, intersected with omega r of some final flag that I'm going to call L. Okay. So we want to analyze this intersection. Let's take, so these are all generic flags. Now we can take 2 of them to be transverse. And so we can send F and E to the standard and opposite flags. And then L is just some generic flag that we want to study. So let's first analyze what this omega r of L is, because R is a really simple partition, so it's not that hard to write down. It's one part. So just by unraveling the definition of Schubert variety again, this is the set of all points of the Grassmannian for which the dimension of V intersect some part of L. Let me see if I can get it right. Is greater than or equal to 1. Let me check that. Yep. Okay, so that's just saying it intersects one specific subvariety of L in at least the line. And then it has to satisfy the conditions for these two Schubert varieties. So let's now look at a picture of two partitions, mu and lambda, that when you take the complement forms a horizontal strip. So here I'm going to make mu be 2, 1. So here's where I'm going to need my colored chalk. Here's mu, and here's lambda. And so say there, when you put lambda in the corner, the complement is a horizontal strip. Then I want to just analyze what the matrices look like, what the Schubert cells look like for omega lambda and omega mu of the standard and opposite flag. So for omega lambda of the standard flag, actually, to be consistent with this, since I have mu in the upper left, I want mu to correspond to the standard flag and lambda to the opposite, if that's okay, just to make the notation nice. Okay, so let's do omega mu first. So omega mu looks like the top Schubert cell is going to be, you draw the staircase, you shift over by 0, then 1, then 2 to find where the 1s are, and then you draw the remaining stars that aren't killed by these. Okay, and then omega lambda of the opposite flag is drawn the other way. So this is like what we did in the duality theorem. So you can find where the 1s are. And now we have stars to the upper left. Okay. And now I'm going to look at sort of the intersection of these. And here I'm going to do another, leave it to you to do the details kind of proof. By the way, the duality theorem proof, the sketch of the proof that I had last time, I have the full rigorous proof in the lecture notes if you're curious. And so I'm leaving it as an exercise for you to do the same kind of thing for the Pierre theorem. But I'm going to outline what the basic ideas are. So I want to consider sort of the overlap of where there's non-zero entries in these two matrices. I want to consider, I'm just going to put stars there even if it's 1, right? So in these two entries, there's non-zero entries in both matrices, also here. And then in the top row, we have 3, which kind of looks like our horizontal strip, right? So we have 2 boxes here, and 1 and 1, and we just add another box to them to expand it into the full matrix. So we should have a total of k plus r stars here. And basically, if we actually have this condition in general that this is a horizontal strip, the stars of this matrix are in their own columns. And otherwise, they're not. Okay. So then we can use this to understand the intersection with this omega r of L just based on the dimension of L. So now everything's going to come out. Okay, so I'm going to let C sub I be the span of the possible values of the ith row of this matrix. Let's call this matrix M. This is the subspace given by the ith row of M. And then let C be the subspace of C to the n defined as the linear combination of these spaces. Okay. So here's your first actual exercise in order to prove the Peary rule. You want to show that if V is in the intersection of these Schubert varieties, then it's a subset of C. Which is basically saying that, you know, the intersection of the pictures really does tell us what the vector spaces look like. And then, and now suppose, so we'll do a little casework here. So if the shape is not a horizontal strip, let's see what goes wrong. Well, then these C sub i's, these rows, have some overlap, and so their sum doesn't have the expected dimension, right? So then the dimension of C is, at most, the total number of stars minus 1. And that's bad news because the dimension of this subspace of the L flag that we're looking at is this subscript, right? N minus k plus 1 minus r, that's the dimension of that flag piece. So n minus k plus 1 minus r is, well, it's n minus k plus 1 minus r. And then now say we have a V that's in the whole intersection, right? We know it intersects L with dimension at least 1, and it is contained in C, but the dimensions just don't add up, right? So, you know, this is n minus this dimension, and so there's not enough room for V. Okay, so that shows it's empty in the case when it's not a horizontal strip, so that term doesn't appear in the Peary expansion. And then what if it is a horizontal strip? Well, now C, this dimension, the dimension of C is what you expect. That's just the number of stars, r plus k. Now we do have the right dimension, and so we have, you know, dimension of this L space intersected with C is 1. So because it's a generic flag, we chose it to be generic, so we can assume it has the expected dimension. So there's a vector u in their intersection, and so say V is in the intersection, it intersects L with dimension 1, and you can actually show, here's another exercise showing that not only is V contained in C, but in this case that V is the direct sum of its intersections with each of the CI's, and those are all one-dimensional. So then you just break up U into, so C in this case is a direct sum of the CI's, and you break up U into its direct sum components, and then V's direct sum components have to be the things that span V. Okay, so that's a sketch. I didn't put all the details in there, but basically V is determined uniquely in the case when it's a horizontal strip. So we get a coefficient of 1 there. Okay. So now we have the Pierre rule, which means we know exactly what the ring is. The cohomology ring is isomorphic to the symmetric function ring. And now we get to do a lot of fun combinatorics to actually compute intersections. Okay, so we're going to talk about the Littlewood-Richardson rule now. And I better actually put some notation in. From now on, I'll just write LR to write Littlewood-Richardson, so I don't have to write the whole thing out. I might even say LR to save time. So we want to understand something a little more general than the Littlewood-Richardson rule most people are familiar with, because we want to understand the intersections of multiple Schubert varieties. So we want to multiply a whole bunch of Schubert classes for different partitions and see how it expands as a sum of these. So I'm going to call the coefficient C nu, and sometimes I'll write, if I have a sequence of partitions like this, which I'm indexing with upper subscripts because I don't want to confuse it with the parts of the partition, then I'm going to just put a bullet to indicate that sequence of partitions. Just like we do for flags. Okay, so we want to understand these coefficients. And these are we know there's the same coefficients as the corresponding expansion of Schur functions now. Sum over nu. And so there's lots of different Littlewood-Richardson rules to actually compute these coefficients. The one that I'm going to do is sort of the classical one in terms of tableaux that have the Yamanouchi property. But there's lots of different, there's things involving Knudsen and Tau's puzzles, and just like things involving Jodot-Duquesne, which I might get to. But let's just talk about the classical one. So what's a Littlewood-Richardson tableau? So I'm going to just really quickly, we already saw semi-standard Young tableau in Jeff's class, but I'll just say it one more time really quickly because I'm using English notation, so I don't want to confuse rows and columns. So let me just draw one. Okay, so here's a skew tableau in English notation where we say it's semi-standard. SSYT is semi-standard Young tableau. If the entries are weakly increasing across rows and strictly increasing down columns. So just flipped upside down from what we're used to. We also say that, so this is skew shape, nu over lambda. Here nu is 653. And lambda is 3, 2. And we're going to define its reading word. To be the word formed by putting into French notation and then reading the word, which is the easiest way to say it. But otherwise, you have to say you concatenate the rows from bottom to top and left to right. So I like to think, flip it upside down. Now this will be the top row. So we read 1, 3, 4, and then 2, 2, 3, and 1, 1, 1. Okay, so this is proof that French notation is better. But again, I apologize for. Okay, so then we also need the content of a tableau. So the content is just the vector alpha sub I, where alpha I is the number of i's in the tableau. So for instance, the content of that tableau over there is, how many ones are there? There's 4 ones, 2 3s, 2 2s, and a 4. So the content is 4, what did I say? 2? 2, 1. Okay. So notice that this has content that's actually a partition. It's decreasing, and that's something that we're going to need too. So sometimes we call the content mu if it's a partition instead of alpha. And then we say that, so here's the big definition. So the reading word is said to be Yamanouchi, which is also called lattice and also called ballot. So you'll see it all ways. If every suffix has partition content, so every final substring or suffix of the word has partition content, means number of i's is bigger than number of I plus 1s. So one reason it's called lattice is a lattice walk sometimes is like a dict path when you can't have a 2 before you have a 1. If you just have 1s and 2s, this is the number of words for which you'll never outweigh the 1s by the 2s. So if you're doing up-down walks, you'll never go below the axis. If a 1 is up and a 2 is down, you'll sort of always stay above. So that's the reason it's sometimes called lattice. I'm not sure why it's called ballot, actually. Does anybody know? What's that? Sorry, I was doing prefixes for lattice words, but then I should have written it backwards. So here this word is 1, 2, 1, 1, 2, 2. There we go. So yeah, so what I mean is this prefix has to, suffix has to have more 1s than 2s, and so does this one, and so does this one at every step. But then that has to be true for all pairs, all adjacent pairs of letters for it to be Yamanouchi. Thanks. Yeah. Yeah, it's very important. Yeah, you can definitely be equal. For instance, 2, 1, I was allowed to put. Yeah.
It's called ballot because you want the number candidate 1 to have at least as many votes as candidate 2, at least as many votes as candidate 3 at each step of the.
So like a voting system.
Yeah.
Okay, there you go. That's why it's called ballot. Cool. Yeah, so the basic Littlewood-Richardson rule is so just for multiplying two shear functions together, so C, we're going to have C lambda with just C mu with 2 partitions, lambda and mu, is the number of semi-standard Yamanouchi tableau of shape nu over lambda and content mu. So for instance, the one that I wrote here is not Yamanouchi. Can anybody see why? Why is this not Yamanouchi?
3 comes before the 2.
The 3, yeah. So if we read this backwards, 1, 1, 1, 3, I have a 3 before a 2. So that, sorry, this is no good. But I can turn it into a Yamanouchi tableau pretty easily. And let's just do an example where we actually compute a Littlewood-Richardson coefficient for these shapes and mu being 5, 3, 1, let's say. So you could easily just kind of see how many there are. So the inner shape is still 3, 2. The outer shape is still 3, 3, 3. I guess, sorry, I mean 6, 5, 3. And then to fill it with 5 1s and 3 2s and 1 3, the top row always has to be 1s because it has to start with a 1 in reverse direction. Similarly, this has to end in a 2, just like that 3 couldn't be there. And then this has to be 2 by semi-standardness. We have an ambiguity here. This could be either a 1 or a 2. We don't know yet. And then we have 1 3. Well, that has to go here because it's a semi-standard tableau. And so then we just have, what do we have left? We have 2 1s and 1 2 left to choose from. So we could either fill it like this or with a 2 down here. And then you just have to check that both of these possibilities still satisfy the ballot condition, and that's true. So that means that in this case, C nu lambda mu is 2. Okay, so now what about the generalized rule? Well, now we just sort of chain these together. So I'm not going to prove this rule, by the way. It's pretty intense to prove it from the Pierre rule. You can find the proof in any of the symmetric function theory books. Stanley has it, Fulton's book, I think Sagan's book has it. Maybe McDonald, too, I think, probably. No? Yeah, I'm not sure about McDonald. Okay, so to generalize this, we want to multiply, I'm just going to multiply 3 together. And you'll see how it goes. So let's do S mu times S lambda times S rho 2 at a time. So let's first multiply these using the Littlewood-Richardson rule. And then multiply this by S rho. And let's expand this out, put the S rho in every term, and multiply these using the Littlewood-Richardson rule then. So then we have, this is a sum over nu. I'm going to call it, chose a good letter here, yeah, tau. So this product, S nu times S rho, is the sum over, say, tau of C tau nu rho S tau. Okay, and then, of course, since we're combinatorialists, we always interchange the order of summation. And so we multiply everything through. We sum over tau first instead. That's our biggest partition. And then we have this product, and then sum over nu, which is going to be contained in tau, but we don't actually need it because our coefficients will be 0 when they need to be, of this product. Okay, so then that means that this summation should be, so we know that that's equal to C tau nu lambda rho is this sum over nu of C nu lambda times C tau nu rho. Okay. So what does this mean combinatorially? So it means that we're going to build up. So first, let's say this guy tells us, so we're summing over nu now. So we don't know the outer shape of whatever Yamanouchi tableau that this counts. So what we're going to do is start with our inner shape lambda. And then we want to extend it by some Yamanouchi tableau of content mu, where we have no idea what the outer shape is going to be when we're done. It can be at whatever we like. So this is going to have content mu and outer shape something, which we can call nu. And then we want to extend it again. Once we've chosen that, now we have our inner shape nu. We want to extend by a tableau of content rho so that the total shape now is fixed. It has to be tau. So we have tau sitting out here somewhere. And we need to fill the rest with a Yamanouchi tableau of content So this looks like a chain, and we can chain them together as much as we want in general, just by using that same summation trick. And there's one more trick to say. This is we used to have this be just an empty tableau in the usual Littlewood-Richardson rule, right? We usually just say, well, this is empty, and now we put our real tableau on top of it. But actually, I want to think of this also as a Yamanouchi tableau of content lambda. And there's actually only one of those. So if you have a straight shape means not skew. Littlewood-Richardson tableau of content lambda, well, the first row has to be all ones. And since you can't put any ones below it, then all the ones have to be in the first row. So the first row actually has to have length lambda 1 and be that row. And then the second row, similarly now, the 2's aren't in the first row because that would make it not Yamanouchi. So now all the 2's have to be in the second row. And that has to be lambda 2 in length, and so on. So this is the unique straight shape tableau that's Littlewood-Richardson of content, what is it? Whatever I drew here, 6, 4, 3, 3 or something. Okay, so now that makes it a little more uniform, because now I can just fill tau with a chain of Littlewood-Richardson tableau, starting with a straight shape, which happens to be unique, and then extending it by a content mu1 and a content rho 1, and so on. And if I had more, I would just break this up even further, break tau up into further subdivisions. Okay, so let's just write down everything I said. Okay. Yeah, so we can define a chain of skew tableau is a list, say T1, T2, up to T sub something, for which so that they're disjoint, so the shapes are all disjoint. And the partial unions, T1 union T2 up to any T sub I, is always a partition shape. So it's important to note that as we're extending this, we can't extend mu so that it looks like this or something, that it's just sort of hanging off the edge. And then we kind of, because then the rest of it wouldn't be a partition shape when we take lambda union mu. So then the generalized Littlewood-Richardson rule can say that C nu lambda 1 through lambda r is the number of chains of Yamanouchi tableau of contents lambda 1 through lambda r that fill the total shape nu. Okay, so that's going to come in handy now. We can start solving our Schubert calculus problems combinatorially. So let's do an example with, again, the 3x4 box that we usually work in. So let's make our four partitions be lambda 1 is, I'm going to take 2, 1, and another 2, 1. And I'll have my third partition be 3, 1. And my fourth partition is just going to be 2. And I want to see how many ways can we fill the 3 by 4 grid with this. Okay. So here, new is the important box. Say. Okay, so to start off, we know that the inner shape here, the first shape is 2, 1, by what we just proved about uniqueness. That's lambda 1. It has to be filled with 1, 1, and 2, if you want to know the numbers. And then we can also get rid of something by symmetry, actually. The last tableau of shape 2, the only Littlewood-Richardson tableau it can be is 1, 1 in the corner like that. Right? It has 2 1s, and they can't be on top of each other, and it has to be in the corner. So we also know this tableau, actually. And now we just have 2 tableaux of contents. We're going to have 2 1s and a 2 in the first one, and 3 1s and a 2 in the other one. So here, I'll make this blue. Can you guys see that color, or should I use a different one? Not really. Let's see. I didn't use green yet, right? That should be nicer. I'll use pink. Ah, that's better. Okay. And, oh, sorry, that's this one. I want this one to be my green. That's the content that I'm filling with. I have 2 1s and a 2. And now I have 3 1s and a 2 that I'm filling after it. So you have to just to analyze how many ways can we put 2 1s and a 2 in here. Well, that's one way. You know, you can put that Littlewood-Richardson rule, Littlewood-Richardson tableau here, and then there is a solution for the second one. And you can kind of just go through all the possibilities. And there's not that many of them. So that's the only possibility for 1, 1, and 2 here. You can also have the 2 way down there, if you want, and then fill the rest with this pink tableau. You could also have here, I claim there's 5 of them. Finish the answer. And by the way, the first time I did this problem, I had it on the lecture notes, the first draft of the lecture notes, I had 4 of them, because I just did it really quickly by hand, and I missed one. And then I was revising them, and I found a 5th one. And then I'm like, OK, how do I know I have them all? So I checked it on Sage, and it's 5. So when in doubt, go to Sage. OK, so then you can also have the 3 boxes being like that. Instead of, if you don't have 1, 1 in the top, you can have 1, 2, 1. You can also have 1, 1, 2. You couldn't put the 2 up at the front, though, because it's Littlewood-Richardson. It has to be the lattice condition. And then there's an interesting thing that happens in that you can't actually have... So here's something that you can't do, actually. You can't have the green tableau in this position, because then the pink one would have to be in this box, and it would have 3 1s. And you're going to, by pigeonhole, have 2 1s in the same column somewhere. So you're in trouble there. So you can't do that. The only other possibility is actually when you have these 3, it is OK. Then you can have a 1 and a 2 here, and your 2 1s down there. And this gets filled in the same way. So it's a little cumbersome. Sometimes it's faster to just get out Sage and multiply the Schur polynomials, honestly. But this comes in handy when you're trying to prove things about Schubert varieties, and you're trying to just work with them from an actual combinatorial perspective. It gives you a bijective thing to work with. So now let's actually go to problem 4 on the Schubert calculus quiz that we started with, and just compute it. This one's going to be a lot easier than that example. So we had translated the problem of 4 lines in 3 space and how many lines pass through all 4 of them into the intersection problem in the Grassmannian that's in terms of Schubert classes is just the multiplication of 4 single box Schubert classes. And we want to show this is 2 points, right? So we want to show this is 2 times sigma of the whole box. This is something worth remembering, is when you have your, so remember we're working in GR42, and the important box is 2 by 2. So the class of the whole box is always just 1 point, because the codimension is 0. So we want this Littlewood-Richardson coefficient to be 2. So we want to calculate C box. So here's what we're checking. C box sub 4 little boxes. And so this is the number of ways of filling in a 2 by 2 square with 4 Littlewood-Richardson tableau of contents 1, right? With a chain of the Yamanuchi tableau of content 1 each. So we really just have 4 different colored ones that we're filling the tableau with. Okay. So my first one has to be in the corner. My second one can be 2 places, right? It can either be here or there. And then the third one is determined, because you're extending the shape each time. And then the fourth one is still in the corner. Okay. So there's the 2. Okay. So sometimes these are written in bijection with, when you only have 1 box each time, it's very common to write this as 1, 2, 3, 4, even though that is confusing because this is not a Littlewood-Richardson tableau. This is a chain of Littlewood-Richardson tableau where I'm just thinking of orange as 2 and green as 3 and purple as 4. So you can put this in bijection, though, with the standard Young tableau of the total shape. And that's a nice trick. And so this gives rise to a number of intersection problems that are nice to solve. In fact, problem 5 on the Schubert calculus quiz, which I'll restate out loud. This really complicated sounding one. How many k-dimensional subspaces of C to the n intersect each of k times n minus k subspaces, given subspaces of dimension n minus k non-trivially? So it turns out, it's still an exercise for you to do this, but maybe some of you have already done it. So problem 5 from day 1 is actually just the Littlewood-Richardson coefficient, where you take your k by n minus k box and you fill it with single box shapes. Okay. So the answer then is going to be the number by this association, right? This bijection here. It's the number of standard Young tableau of the total shape, meaning semi-standard with content 1, 1, 1, 1. And for that, it's worth mentioning a very classical result called the hook length formula, which makes things a lot faster. So this was proven by Frame, Robinson, and Thrall, I believe. So the hook length formula just says the number of standard Young tableau of shape, of some given shape, any outer shape nu, is the size. So let's say size of nu is n. It's n factorial over the product of all the hook lengths in the diagram. So if we have, just as a simple example, let's make it a little bit bigger. The hook lengths are you pick a box and travel south and east until you can't anymore and count how many boxes you have. So here we have 4. In this box, we would have 3 in our hook. This one has 1, this one has 2, and this one has 1. So we would do 5 factorial over 4 times 3 times 1 times 2 times 1. So in the case of this problem, we actually have an even easier solution now. It's 4 factorial divided by the product of these hook lengths, which is 3. We have 2 2s and a 1, which is 2. Okay. So lots of different ways of getting the same thing. And now you can solve general zero-dimensional intersection problems. You can compute in the cohomology for any shapes, because now we know how to multiply shear functions together. Okay, so now in the last half hour, I'm going to switch. This kind of sort of finishes the picture of the Grassmannian. Linear intersection problems in space are basically all described by this combinatorics. But there's variations. We were talking about, I called it variations on a theme of Schubert calculus. So if this is the theme, or maybe variation 1, as you want to call it, the next variation that I want to talk about is the flag variety instead of the Grassmannian. So here's a variation. Okay, so we're going to let FL sub n be the set of all complete flags in Cn, C to the n. Okay, so as a set, that's a set. Remember, the Grassmannian was a set of k-planes in n-dimensional space. So this is some sort of, not generalization, but there's some kind of map between these things that we'll talk about later. So how do we understand this the way we did with the Grassmannian, the way we did this with the projective space? Well, we want to understand this as some quotient by looking at matrices. So each flag can be represented as the partial row spans of some matrix. An n by n matrix. For instance, have a 3 by 3 matrix here. Okay. I should say an n by n matrix with determinant non-zero. So something in GLN. So if it has determinant non-zero, we can take the span of this row as F1, and then the span of the first 2 rows as F2. That's a linear subspace containing the first. And then the span of the first 3 rows as F3. And we get a complete flag. And F0 is 0, as usual. Okay. So then we can ask what row operations don't leave this flag fixed, right? So in the Grassmannian, we were allowed to do any elementary row operations, but now we have to be careful because if we add this row to this row, that's going to change F1, right? So that doesn't stabilize our flag. So what the operations that we're allowed to do are the this is fixed by, you can still scale a row or adding a row to a later row. Because you can add down and still not change the flag that you're in, because we're doing partial row spans from the top. So this is equivalent, and we're going to get to the Borel subalgebras and how you quotient by a Borel, and this is exactly what this is doing. But we're going to first just think of it as an equivalence relation generated by these operations, and talk about the flag variety as GLN mod this equivalence relation. Okay. So now we have a topology, just like we had before, by the quotient topology. And we can talk about, so now that we have these operations, we want to do some kind of row reduction in the flag variety. And this is not a row reduction that they teach in high school, but let's just do it. So what we're going to basically do is, to find our Schubert cells, so we want to find the leftmost non-zero entry in the first row. Scale the first row so that that's a 1. So we're going to make this the that 2 the pivot. And okay, so I'm going to make this 1.5. And then we can use that 1 to clear its column. So, because we can add downwards. So clear the column of that 1. And then we're going to continue on the other rows. Okay, so let's just do it for this example. If we subtract this row from this row, we get 2.5 here. We get, we're going to multiply this by 2 to subtract it from here. And we get -6 in this entry. And then now we do the same thing on the second row. And we get this as our pivot. So here's our pivot, and we subtract it from the second row, and then we'll be done. And we'll get -6 here, which we scale to 1. And so our final form is going to look something like this, which I'm going to draw as a Schubert cell with stars in the non-zero entries. So all the other entries have to be 0 by the positions of our 1s. Everything to the left or below a 1 is a 0. But then we have these leftover possible entries after we do. So the general form for one of these is actually you take a permutation matrix of 1s, since there's only 1 1 in every row and column, and then the zeros are to the left and below them, which is really cool. So in the Grassmannian, we had partitions indexing our Schubert cells. In the flag variety, we have permutations instead. So here's another example. Oh, and I need to say what I'm calling this Schubert cell. So I'm going to call this, instead of omega, I'm going to use x for the flag variety. XW circle, where W is going to be the permutation. The way I'm going to read the permutation to make it consistent with the way I did the Grassmannian is the columns are going from right to left. So I'm going to count the distance from the right of each one. So 2, 3, 1. Is the permutation that I associate with this. Okay. Okay, so so let's draw another one and look at its dimension and stuff. So the cell 4, 5, 1, 3, 2 is going to be a 5 by 5 matrix here, as we're in a permutation of 5. And we're going to draw the first one 4 4 spaces from the right, the next one 5 spaces from the right, then 1 from the right, and 3 and 2. And then we're going to kill all things to the left of any 1 and below any 1. And after we're done, below, we end up with a number of stars. Okay. And so we can, just like we did for the Schubert cells in the Grassmannian, we can write down explicitly what these are, of W. It's going to be the set of flags now, V dot, in the flag variety, with some dimensional, some intersection conditions with the standard flag. So the intersection of the pth part of V with the qth part of F, just by looking at it, you can check that this is equivalent to the star diagram. It's going to be the number of indices I less than or equal to P, for which W of I is at most Q for all P and Q. So that's some algebraic description. And then we can generalize this to arbitrary flags. Say use the flag E instead. That's just replacing this F intersection with whatever flag you want. So here, this is the standard flag. That corresponds to these diagrams, but then of course you can change basis, just like we did before. And then we can define the Schubert varieties in the flag variety. Again, exactly like what we did in the Grassmannian, now we take XW to be the closure of the Schubert cell. And I think, no, I don't have it as an exercise, but we'll get to it tomorrow as to what Schubert cells these closures contain. So that's coming up later. Okay. Yeah, and one nice thing combinatorially is we can, just like with the partitions, we were able to compute the dimension by just the size of the partition. There's a statistic on permutations that lets us compute how many stars we have. Actually, 2 statistics that are equivalent. So we're going to define inv of a permutation to be the number of pairs of entries in the partition that are swapped. Number of pairs I less than j with W of I greater than Wj. So inv of 4, 5, 1, 3, 2. So what are some inversions here? Can somebody give me an inversion in this? What's that? 4 and 1, right. So this is our first one. We can look for the other ones with 4, right? 4 and 3, 4 and 2. We also have 5 with 1 and 3 and 2. Any others? 3 and 2. Okay, so how many is that? 7. Oh, look, we have 7 stars. What a coincidence. So it's not hard to check. I mean, so what's going on here? When you have 4, 1, this is our 4 and this is our 1, you kind of just go right from the 4 and up from the 1, and that gives you one of your stars. So each one of those stars is literally an inversion, right? If we want the inversion between 4 and 3, that's this star, right? And 4 and 2, and then 5. And this one's that special one between 3 and 2. So you can see where the inversions come from. So the dimension of the flag variety, or the Schubert cell, whichever you like, is the inversion number of the permutation. Now there's also another way of computing the inversion number besides this that's super useful for computing the analog of Schur functions in the flag variety, which are called Schubert polynomials. And that is, so first of all, we're going to define the permutation S sub I to be the permutation that just switches I and I plus 1. So in cycle notation, it's just the transposition I plus 1. And then we're going to define the reflection length, or just the length, of W, denoted L of W, is the minimum, number of, minimum K, such that there exists a decomposition of W into K transpositions. So there exists a decomposition W as SI1 times SI2 up to SIK. So it is an exercise, which if you haven't done it before, you should definitely do this exercise. It's just really fun and really important. So it's all the best things. So the exercise is prove L of W is in of W for all W. Okay. Okay, so now let's make some parallels. I want to get to something that Vivian is going to show you how to compute in Sage this afternoon. So I'll go into more detail on the flag variety tomorrow, but first I just want to make a sort of comparison chart. So we have the Grassmannian versus the flag variety. So we have, our Schubert varieties are omega lambda. Here we have XW for permutations. And then we can ask, what are the cohomology classes of these? So turns out the cohomology ring of the Grassmannian, well, we already know this one. This is this quotient by the bad partitions of the symmetric functions. And then for the flag variety, we can actually also compute its cohomology ring. This is the coinvariant ring that Stephen mentioned in his first talk, I think. So this is the ring of polynomials modded out by E1 through En, the elementary symmetric polynomials. And then you can ask, well, what's the analog? So here we have a basis for the cohomology ring S lambda. What is a nice basis for this ring that corresponds to the cohomology classes, the intersection of the cohomology classes in the flag variety? Well, these are called Schubert polynomials. And they're written math frac S, which looks like a G, but it's an S. And then they're indexed by partitions. So we're going to prove all this about the coinvariant ring being generated by monomials indexed by partitions and by Schubert polynomials tomorrow. But right now I want to define the Schubert polynomials so you can do computations with them. So we can just define them, just like symmetric functions. This is independent of flag varieties and everything as far as just defining them goes. So we're actually going to start by defining them recursively using symmetric difference operators. So there's a number of different definitions, just like there are for the Schur functions now. But I'm going to start with the symmetric difference operators, which is sort of the original way they were defined. So the symmetric difference operator, partial sub I, I'll call it, is the operator that takes a polynomial in some number of variables and returns. So the operation is you're going to take the polynomial, subtract the result of switching I and I plus 1, xi and xi plus 1 in the polynomial, and then dividing the result by xi minus xi plus 1. Okay, so the cool thing is that this is still a polynomial. Okay, so why is that? Well, let's just do an example. So partial sub 2 of, here's a good example. so we're going to apply it. We can apply it on each monomial separately because it's additive, but we can do the whole thing for now. So we take the polynomial p, and we subtract si of p means switch xi and xi plus 1. So we're going to switch x2 and x3 here. And in the first monomial, if you switch x2 and x3, we get x1 squared, x2, x3 to the fourth. And then if we switch x2 and x3 in this monomial, we get 2x1, x3. And then nothing happens to the x4 squared. So first of all, you can see that if there's no x2 in your polynomial or no x3, then it just dies. And so this is very similar to a derivative, actually. The sort of things that don't involve your variable automatically cancel. And then we take the rest and we divide it by x2 minus x3. And it's pretty easy to see that one of these monomials paired with its opposite is going to be divisible by x2 minus x3. For instance, here we have we can factor out the x1 squared, and we get, if we factor out x1 squared, x2, x3, we just get, x2 cubed minus x3 cubed? And in general, we'll always get something like this, which is divisible by what we want. And our other term is 2x1, x2 minus x1, x3 is x1, x2 minus x3. Okay, and then you can divide out, So this is going to be the thing you get from geometric series that's homogenized. X2 squared plus x2, x3 plus x3 squared plus 2x1. Okay, so it is always a polynomial. And then we're going to use these symmetric difference operators to define the Schubert polynomials. So first we have to start with a biggest one, and then all of them are going to be derivations of this biggest one. So we're going to define W0 to be the longest permutation, n minus 1, n minus 2, 3, 2, 1. This is called the longest because its length is longest. So inv of W naught, or length of W naught, is n choose 2, which is the largest possible inv, right? So this is called the longest permutation. And we're going to start by defining our Schubert polynomial, curly s, sub W0, to be x1 to the n minus 1, x2 to the n minus 2, down to xn minus 1, and then xn to the 0. So it's just the sort of, you put the exponents n minus 1, n minus 2 down to 1 on the variables, and that's your top Schubert polynomial. And then to define the rest of them, so here's our first definition. And then if you have a permutation W that you want to compute the Schubert polynomial for, we want to basically factor it as this top longest permutation times a bunch of transpositions. This is some minimal representative of this form. So a minimal k. And then we can define SW to be the partial symmetric difference operators of these in reverse order. So we're applying SI1 first and then SIK last. So we do partial IK, partial IK minus 1, down to partial I1 of this one that we defined already. Okay, so I knew I would be a little short on time, but I think Vivian's going to explain a lot more about these, how to compute these. One thing that I think I can say in the last 5 minutes is that there's a very interesting stability theorem, which is that if you have a permutation W in Sn, and you consider it as a permutation of a larger symmetric group Sm, but just by the natural embedding. For instance, if W is like 1, 3, 2, and then we stick a 4 on top, we can always add numbers 4, 5, 6, etc. Then actually the Schubert variety, the Schubert polynomial doesn't change. So if W goes to W prime under this, then SW equals SW prime. That means we can actually sort of define them we can define Schubert polynomials as polynomials associated to infinite permutations with a sort of finite window in which they're actually a permutation. And what this also means, which, so Vivian coded a package in Sage that computes Schubert polynomials, but the way you input them is, it's sort of messy to write out permutations. And the original way they were defined by Lescaut was in terms of codes that encode the permutations. So let me talk a little bit about Lamer codes, which I like to think of as inversion codes because you're encoding how many inversions each number has. So the Lamer code of a permutation it's the sequence alpha 1, alpha 2, etc., where alpha I is the number of inversions in W of the form Wi with Wj to its right. So the number of inversions having that entry as its leftmost entry. So let's do an example for one of the bigger permutations that we had before. I think it was 4, 5, 1, 3, 2. So if we're going to encode how many inversions each number has, well, the 4, we had 3 inversions to its right. And then the 5 also had 3 inversions to its right. The 1 doesn't have any inversions to its right, so that's 0. And then the 3 had 1, just the 2. And then the cool thing is for stability, you can really see the stability here in terms of what the code is. Because if I added a 6 on the end here, all that would do is stick a 0 on the end here. And you can stick as many zeros as you want and just think of them as finite sequences of integers. And this is a bijection, actually, between all finite sequences of positive integers, or sequences of non-negative integers where some tail is all zeros, with permutations where some tail is all the integers. Yeah.
That when earlier you showed the permutation of your matrix, this lemma code is just reading the number of stars in the matrix line by line.
Yes, that too, actually. We had our matrix, which I erased, was like this. With that permutation around, that's 3301. Okay, so the point is, Vivian's package, you'll enter something like Schub of, you define your Schubert polynomials with some algebra declaration, and then you do Schub of 3301, and that means this Schubert polynomial. So when she defines when she shows you your package, that's what it's going to refer to. And so here's your homework assignment for this afternoon. For the exercises session, so what we want to know, since the Schubert polynomials are the analog of Schur functions, we want to know how do you multiply Schubert polynomials together. So we really want to know if you have SW times SV. I didn't say any of this, but the Schubert polynomials form basis of the ring of polynomials. in particular in the coinvariant ring, what is this as a sum of Schubert polynomials, SU with some coefficients, C, U, V, W. The question are, what are these coefficients? So we want like a Littlewood-Richardson rule or something for these coefficients. Turns out this is an open problem. So in Schur functions, we have lots of Littlewood-Richardson rules. There's no explicit combinatorial description of these yet. But we do have the analog of the Peiri rule. And this is called Monk's rule, which tells you exactly how to take just, if W is just a single transposition, an adjacent transposition, and you multiply it by another Schubert polynomial, then what do you get? You're going to get some summation here, I guess some coefficients, C, U, Si, V. And these coefficients are known. So the exercise this afternoon, which I think will give you a lot of practice working with Schubert polynomials and getting a feel for them, is try to conjecture what these coefficients are. And I have this as written out as a problem in the lecture notes and everything. But you can see if you can guess it. This one is known. This is open. But if you want to guess this one too, you're free to do so. So that's all for today, and we'll talk tomorrow.
Are there any questions?
There's like three, wait.
Yeah,
go.
let's start dancing.
Is it at least known if they're positive or the one on top?
Yeah, it is known that they're positive because this is... Yeah, because the geometry. Because if you take the Schubert varieties, the cohomology classes, and you take their cup properties, this corresponds to that. So this is going to be some positive sum of cohomology classes. Yes, it's positive.
But there's no combinatorial proof.
Right.
Because you don't have a rule for it.
Yeah.
Well, I was going to ask something similar, but is there even a combinatorial proof that they are positive without giving like that they are the cardinality of some set?
I don't think so.
Yeah.
Yeah, I think it's still a big open problem.
One thing that is known now, which was just proven in February by Sami Asaf, is a positive combinatorial rule for the coefficients of if you take a Schur function times a Schubert polynomial. And these, I'll say tomorrow why these are special cases, actually, of the
Those were proved by Sotillo.
Yeah, I would say
this was already proven?
before.
Oh, well, there's a new rule out. So this is known, I guess, several ways.
There's a paper, I think, called Schur times Schubert.
Yeah,
Like that.
yeah. Well, was there like a positive counting formula? Or was it just like enumerating them with some minuses?
Positive.
No, I think it's possible.
Oh, was it? Okay, well then
It's not positive for the Muller Nakayama rule. But for the
okay.
Slanga it's positive.
All right. Well, this is known then in many ways.
You can
I
go
guess
to
one
the
remark
top
is
and
that,
then
I don't know if you said that, but a Schur function is one of these Schubert
Yeah.
polynomials. So it's a special case.
Yeah, it's a special case for certain permutations.
You will see that later.
We'll see that later today.
Nice.
You can shake that.
You had a question?
Just, I suppose Monk's rule, if V is Rosmanian, is like multiplication by a box, right?
If V is, I'm not sure.
I mean, I'm just wondering, probably the
Box.
Gary's rule is like, no, I mean, SI.
Oh. Oh, I see. Yeah, no, SI.
is the class of a box, the Rosmanian biplane.
Yeah, SI is it's always going to be in the first cohomology group. So I guess it is.
Presumably there's some rule that's like
Oh.
Gary's rule is like,
Yeah, the different facility has one. It
Yeah.
was conjectured by Billy and Birch around 20 years ago,
Yeah. Yeah.
and proven shortly thereafter.
What the question is just what kind of permutation does SI somehow if you want to
I'm not sure.
you know,
Oh, it's a K-Grassmannian associated to a single row, which apparently we'll talk about later.
so is it easy to say like in terms of cycle structure or something?
guys, it's been a couple of years. It's kind of an ugly, like, an ugly formula, but it's like easy to.
We can talk about that afterwards. Yeah. Any other questions? No? Okay, so we're going to break for lunch. Lunch is 2 hours. We'll be back here in 2 hours. So it's 2:30 for the next stop. And then there'll be an exercise session this afternoon. So bring your laptops ready to go. And also just put on paper. That'll work as well. Have a good lunch. Well, let's again.